Look up at the night sky, past the familiar constellations and the glow of our own Milky Way, and you'll find a cosmic whirlpool of stars, gas, and dust, the Pinwheel Galaxy. Also known as Messier 101, this stunning spiral sits 21 million light-years away, close enough for its swirling arms to dazzle even amateur astronomers. But don't let its beauty fool you. Behind those glittering stars lies a labyrinth of cosmic oddities, phenomena so strange they defy our understanding of the universe. From explosive supernovas to mysterious dark matter halos, the Pinwheel Galaxy holds secrets that challenge everything we think we know about space. What makes this galaxy so special? For starters, it's a hotbed of stellar chaos. Imagine a place where stars are born in frenzied bursts, where black holes lurk unseen, and where entire regions glow with energies we can't yet explain. This isn't just another pretty face in the cosmos, it's a cosmic detective story, packed with clues waiting to be unraveled. And today, we're diving deep into 30 of its most jaw-dropping mysteries. Some will leave you in awe, others might send a chill down your spine, because the Pinwheel Galaxy doesn't just whisper its secrets, it shouts them across the void, daring us to listen. This isn't just a tour of distant wonders, it's a journey into the unknown, a chance to stand at the edge of human knowledge and peer into the abyss. Every strange phenomenon we uncover raises new questions, pushing the boundaries of science and imagination. So buckle up. By the time we're done, you'll never look at this galactic pinwheel the same way again. The universe is stranger than we've ever dreamed, and the Pinwheel Galaxy is here to prove it. At the heart of the Pinwheel Galaxy, where most spiral galaxies host a ravenous supermassive black hole, something peculiar unfolds silence. While other galactic cores roar with violent energy, spewing jets of radiation and consuming matter in a cosmic feeding frenzy, this one sits eerily still. Scientists call it an anemic black hole, a lightweight compared to the beasts found in galaxies like Messier 87, home to the famous first ever photographed black hole. But why is the pinwheel's center so quiet? One theory suggests it's starving. Unlike active galactic nuclei that gorge on swirling gas and shredded stars, this black hole might simply lack a steady meal ticket. Imagine a bear hibernating through winter. Its metabolism slows when food is scarce. The pinwheel's black hole could be in a similar cosmic slumber, biding its time until fresh material stumbles into its grasp. Another idea points to its surprisingly modest size. Weighing in at around 1 million solar masses, it's a featherweight compared to the billion solar mass titans found elsewhere. Could its small stature explain its subdued behavior? But the real mystery isn't just why it's quiet, it's what this means for the galaxy itself. Black holes aren't just destructive monsters, they're cosmic architects shaping their galaxies through powerful feedback loops. Jets and radiation from active black holes can heat surrounding gas, stifling star formation. So if the pinwheel's black hole isn't stirring the pot, does that explain why its spiral arms brim with newborn stars? Some researchers argue this dormancy might even be temporary. A single gas-rich collision could wake the beast, transforming the galaxy's core into a fireworks show of X-rays and relativistic jets. Until then, this sleeping giant offers a rare glimpse into a cosmic calm, one that challenges our understanding of how black holes and galaxies evolve together. This anomaly raises even deeper questions. Are quiet black holes like this the rule or the exception? Could the pinwheel be showing us a phase every galaxy passes through, a lull between outbursts of chaos? The more we study its silent core, the more we realize how much we still don't know about the delicate dance between black holes and the galaxies they call home. Now let's venture beyond the galaxy's quiet core and into one of the most baffling cosmic puzzles: dark matter, or rather, the apparent lack of it. the Pinwheel Galaxy should be cloaked in a massive halo of this invisible substance, just like every other spiral galaxy we've studied. Dark matter's gravitational pull is what keeps galaxies from flying apart as they spin, acting like cosmic glue. But here's the twist: when scientists measured the pinwheel's rotation, something didn't add up. The numbers suggested far less dark matter than expected, as if someone had quietly siphoned it away. How could this be? One camp argues our measurements might be off. Calculating dark matter isn't easy. It doesn't emit light or interact with normal matter except through gravity. Maybe we're misreading the pinwheel's unique structure, its sprawling arms distorting our calculations. Others propose a radical idea. What if the pinwheel simply formed differently? Most galaxies are thought to emerge from dense clouds of dark matter, but perhaps this one assembled in a quieter corner of the universe where dark matter was thinner. Imagine building a sandcastle with less sand. The structure might look the same, but it's fundamentally lighter. Then there's the elephant in the room. If the pinwheel truly has less dark matter, does that mean our entire understanding of galaxies is flawed? For decades, dark matter has been the cornerstone of galactic physics, explaining why galaxies don't tear themselves apart. If this galaxy defies the rule, it could force us to rethink everything. Some theorists even speculate that alternative theories of gravity, like modified Newtonian dynamics, might explain the anomaly, though these ideas come with their own set of complications. The mystery deepens when you consider the pinwheel's neighbors. Surrounding galaxies show normal dark matter levels, making its deficit even stranger. It's like finding one house in a neighborhood where gravity works differently. Could tidal forces, gravitational tugs from nearby galaxies, have stripped away its dark matter? Or is the pinwheel hiding it somehow, tucked away in regions we can't yet detect? Every answer leads to more questions, and that's what makes this enigma so thrilling. The pinwheel isn't just challenging our assumptions, it's daring us to question the very framework of modern astrophysics. What's clear is this: the Pinwheel Galaxy refuses to play by the rules. Whether it's a measurement error, a cosmic oddity, or a sign of deeper truths waiting to be uncovered, one thing's certain: the universe loves keeping us on our toes. And as we peel back the layers of this mystery, we're not just studying a galaxy, we're testing the limits of human knowledge itself. Deep within the Pinwheel Galaxy's spiral arms, astronomers have spotted something that shouldn't be there: a colossal bubble of hydrogen gas stretching thousands of light years across and expanding at breakneck speeds. Picture a soap bubble blown by a cosmic giant, except this one isn't delicate or fleeting. It's a raging, turbulent structure, hurling material outward with enough force to reshape its corner of the galaxy. What could possibly create such a monstrous phenomenon? The answer might lie in two of the universe's most violent events: supernovas or the outbursts of an active galactic nucleus. Supernovas are the obvious suspects. When a massive star explodes, it doesn't go quietly. The blast unleashes shockwaves that rip through surrounding gas, carving out cavities and pushing material outward like a snowplow clearing a road. If multiple stars exploded in close succession, their combined energy could sculpt a bubble of this scale. Imagine a series of fireworks detonating in sync. Each explosion amplifies the last, creating a shockwave far more powerful than any single blast. Some researchers point to the pinwheel's rich star-forming regions as evidence. These stellar nurseries produce short-lived, massive stars that die young and explosively, making them prime candidates for bubble-building duty. But there's a twist. The bubble's sheer size and energy have others questioning whether a supernova alone could be responsible. That's where the galaxy's dormant black hole re-enters the story. While it's quiet now, what if it wasn't always? Active galactic nuclei, awakened black holes, can unleash jets of plasma with enough power to inflate structures like this in mere cosmic moments. Even a brief outburst thousands of years ago might have left this lingering imprint. Think of it as a ghostly echo of past fury, a reminder that the pinwheel's calm exterior might hide a volatile history. The bubble isn't just a fossil, though. It's still shaping its surroundings. As it expands, it compresses nearby gas, triggering new star formation in its wake. This creates a paradoxical cycle, destruction birthing creation. The same forces that tore a hole in the galaxy's disk might also be seeding its next generation of stars. It's a reminder that in the cosmos, chaos and creativity are often two sides of the same coin. So which explanation holds the key? The truth might be messier and more fascinating than either scenario alone. Perhaps it's a combination of supernovas and past black hole activity, a 1-2 punch of cosmic violence. Or maybe there's an entirely different mechanism at play, something we haven't yet imagined. That's the beauty of the Pinwheel Galaxy. Every answer peels back another layer of mystery, reminding us just how much we have left to discover. Scattered throughout the Pinwheel Galaxy like cosmic lighthouses, ultraluminous X-ray sources, or ULKs, defy easy explanation. These enigmatic objects blaze with X-rays millions of times brighter than our Sun, yet they're not quite as powerful as the radiation spewing from active galactic nuclei. They occupy a strange middle ground, brighter than typical stellar mass black holes but dimmer than supermassive ones. And the Pinwheel Galaxy happens to host an unusually high number of them, turning this cosmic whirlpool into a laboratory for one of modern astronomy's most heated debates. So what exactly are ULXs? The leading theory suggests they might be intermediate mass black holes, a long-sought missing link in the black hole family. Stellar mass black holes form from collapsed stars and typically weigh up to a few dozen times our Sun's mass. Supermassive ones, like the beast at our Milky Way center, tip the scales at millions or even billions of solar masses. But intermediate mass black holes, predicted to weigh hundreds or thousands of suns, have been frustratingly elusive. ULXs could finally be the smoking gun. Imagine finding a species between a wolf and a blue whale, something that rewrites our understanding of cosmic evolution. Not everyone's convinced, though. Some scientists argue these X-ray powerhouses might actually be ordinary stellar mass black holes with a trick up their sleeves. If a black hole's accretion disk, the swirling disk of superheated gas feeding it, isn't perfectly aligned with our view, radiation could be focused into a narrow beam like a flashlight pointed straight at us. From our perspective, this beaming effect would make the black hole appear far brighter than it truly is. It's the cosmic equivalent of mistaking a car's headlight for a spotlight. The Pinwheel's ULXs add another layer of intrigue. Many sit near star-forming regions where massive stars live fast and die young. This fuels speculation that some might be neutron stars, ultra-dense stellar corpses gorging on gas at unprecedented rates. In 2016, astronomers actually caught one ULX pulsing, a telltale sign of a neutron star's magnetic field. That discovery threw a wrench in the intermediate mass black hole theory, proving some ULXs are smaller objects behaving in extraordinary ways. The stakes here are huge. If ULXs are intermediate mass black holes, they could reveal how supermassive giants grow. If they're beamed stellar remnants, they'd force us to rethink how black holes and neutron stars interact with their environments. Either way, the Pinwheel's abundance of these objects makes it a cosmic Rosetta Stone, a key to decoding some of the universe's most persistent mysteries. Every flicker of X-ray light carries clues, and astronomers are watching closely, ready for the next breakthrough that could upend our understanding of these brilliant enigmas. Among the Pinwheel Galaxy's many riddles, one stands out as particularly perplexing: the case of the missing red supergiants. These colossal stars, the swollen final act of massive stellar lives, should be abundant in the galaxy's bustling star-forming regions. Yet when astronomers peer into those cosmic nurseries, they find far fewer of these crimson giants than expected. It's as if the Pinwheel has a hidden stellar graveyard, quietly vanishing stars before they reach their final fiery chapter. The absence strikes at the heart of stellar evolution models. Red supergiants form when massive stars, those at least 8 times heavier than our Sun, exhaust their hydrogen fuel and begin fusing heavier elements. Their outer layers expand dramatically, turning them into bloated, cooler giants that glow with a distinctive red hue. In other galaxies, they're easy to spot, peppering star-forming regions like glowing embers. So why does the pinwheel seem to skip this step? One clue lies in the galaxy's unique metallicity, the abundance of elements heavier than hydrogen and helium. The pinwheel's gas is richer in these metals compared to many galaxies, and that might be throwing a wrench into the usual stellar life cycle. High metallicity changes how stars live and die. More metals make a star's outer layers more opaque, trapping radiation and driving stronger stellar winds. These winds strip away material at a furious pace, potentially preventing the star from ever swelling into a classic red supergiant. Instead, it might shed so much mass that it transitions directly to a hotter, bluer phase or even collapses prematurely into a black hole without the typical red supergiant finale. Think of it like a candle burning too fast. The flame never settles into a steady glow before it's snuffed out. There's another twist. Some of these stars might be hiding in plain sight. Dust, plentiful in metal-rich galaxies like the pinwheel, could be shrouding red supergiants, dimming their light until they're nearly invisible to our telescopes. Or perhaps they're evolving so rapidly that we're simply catching them at an awkward phase, like snapping a single frame of a film and missing the climax. The implications ripple outward. Red supergiants are cosmic alchemists, forging heavy elements in their cores and scattering them across space when they explode as supernovae. If the pinwheel stars are dodging this phase, it could alter the very chemistry of future generations of stars and planets. Even more intriguing, what if this isn't unique to the pinwheel? Could other metal-rich galaxies hide similar gaps in their stellar populations? Each unanswered question tightens the knot of this cosmic mystery, reminding us that even the most well-understood processes in the universe still hold surprises. The pinwheel's red supergiant problem isn't just a missing piece of a puzzle. It's a challenge to our textbooks, a quiet rebellion against the expected script of stellar life and death. And as astronomers keep searching for these absent giants, they're not just studying a galaxy. They're rewriting the story of how stars live, die, and shape the cosmos around them. The Pinwheel Galaxy's spiral arms should be graceful, sweeping curves, perfect textbook examples of cosmic symmetry. But look closer and you'll spot something odd. These arms aren't smooth, they're jagged, twisted in places, as if the galaxy itself has been crumpled like a piece of cosmic paper. These kinks aren't random flaws. They're clues to a violent history of gravitational tug-of-war, likely caused by the galaxy's smaller, unseen companions. Dwarf galaxies orbiting the pinwheel might be the culprits. Though faint, their gravity can warp the larger galaxy's structure over millions of years. Picture a speedboat cutting through calm water. The wake it leaves distorts the surface long after it's passed. Similarly, as these dwarf galaxies swing by the pinwheel, their gravitational wakes pull at the spiral arms, bending stars and gas out of alignment. Some researchers suspect one particular dwarf companion, NGC 5477, might be responsible for the most prominent kink. Its last close encounter could have sent ripples through the pinwheel's disk, leaving these cosmic wrinkles behind. But there's another possibility: dark matter's invisible hand. If the pinwheel's dark matter halo is lopsided, perhaps from an ancient collision, its uneven gravity could twist the arms from within. Imagine trying to spin a pizza dough while someone tugs irregularly at the edges. The result wouldn't be a perfect circle but a distorted shape, much like the pinwheel's warped spiral. The kinks aren't just cosmetic, they're altering the galaxy's evolution. Gas compressed in these bent regions collapses faster, sparking bursts of star formation. Some of the Pinwheel's brightest stellar nurseries sit right along these distorted stretches, as if the galaxy is turning gravitational chaos into new suns. Yet the biggest question remains, are these kinks frozen in time, relics of past encounters, or is the pinwheel still being reshaped today? With every new observation, astronomers piece together a clearer picture of this galactic dance, one where even the smallest partners can leave the most lasting marks. What makes these distortions so fascinating isn't just their cause, but their defiance of expectations. Galaxies like the pinwheel are often portrayed as pristine, symmetrical whirlpools. But reality is messier, more dynamic. Every kink tells a story of near misses, collisions, and cosmic feedback loops that transform structure into something richer, something alive. And as we map these twists, we're not just studying a galaxy's past, we're watching it evolve in real time. Tucked between the Pinwheel Galaxy's spiral arms, a cosmic fugitive streaks through space at unimaginable speeds, an entire star cluster hurtling so fast it could escape the galaxy's gravitational grasp. This isn't just a group of stars drifting lazily through the cosmos. It's a celestial bullet racing at over 2 million miles per hour, flung outward by forces we can only begin to guess at. Hypervelocity clusters are rare, but this one's speed isn't even the strangest thing about it. Its stellar makeup reads like an astronomer's riddle. Young, metal-rich stars packed tightly together, defying the usual rules of how such clusters form. How does an entire cluster get kicked into overdrive? The leading theory points to a gravitational slingshot, a cosmic game of pinball where the cluster ventured too close to the galaxy's supermassive black hole. The black hole's immense gravity could have whipped it outward like a stone from a sling, sending it careening into intergalactic space. But there's a problem: the pinwheel's central black hole is dormant, lacking the violent activity we'd expect from such a dramatic ejection. That leaves another possibility, a close encounter with another massive object, perhaps a dense dark matter clump or even a previously unseen intermediate black hole hiding in the galaxy's outskirts. Imagine an invisible giant swatting a cluster of stars into the void, leaving no trace behind except the speeding cluster itself. Then there's the mystery of its stars. Typically, runaway clusters are ancient relics, born in the early universe and scattered by eons of gravitational encounters. But this one's stars are surprisingly youthful, burning hot and blue with abundances of heavy elements that suggest they formed more recently. Even stranger, they're packed so densely that collisions should be common, yet they're not. It's like finding a bustling nightclub inside a speeding train, with everyone dancing just inches apart but never bumping into one another. One explanation could lie in the cluster's birthplace. If it formed in an unusually dense gas cloud near the galaxy's core, the sheer weight of surrounding material might have compressed it into this tight, stable configuration before something catapulted it outward. Alternatively, it might not be a true cluster at all, but a dwarf galaxy stripped of its outer stars by tidal forces, leaving only its bright core racing through space. The implications are staggering. If clusters like this can be ejected so violently, they could be seeding heavy elements across intergalactic space, enriching the cosmic wilderness with the building blocks of planets and life. And if the pinwheel's quiet black hole really did fling it outward, that would mean even dormant giants can unleash unimaginable power when the conditions are right. Every observation of this rogue cluster peels back another layer of mystery, revealing just how little we understand about the forces shaping our universe. As it streaks toward the void, this stellar outlaw carries more than just speed, it carries secrets. And with each passing moment, it's racing farther from our grasp, a cosmic puzzle slipping into the darkness. In the Pinwheel Galaxy, astronomers once trained their telescopes on a star with all the telltale signs of an impending supernova, a massive, aging giant flickering erratically, its outer layers growing unstable. Everything pointed to an imminent explosion, a stellar finale that would outshine entire galaxies for weeks. Then, without warning, nothing happened. The star didn't just fade, it vanished entirely, leaving behind a ghostly question mark in the cosmos. This wasn't just a missed prediction. It was a cosmic magic trick, and scientists are still scrambling to figure out how the star pulled it off. The leading explanation: a failed supernova, a rare event where a massive star collapses directly into a black hole without the usual fireworks. Normally, when such stars die, their cores implode, triggering a shockwave that blasts the outer layers into space in a spectacular supernova. But sometimes, theory suggests the core's collapse might be so sudden and complete that the rest of the star gets swallowed whole, like a trapdoor snapping shut beneath it. No explosion, no warning, just silence. Imagine lighting a firework fuse only for it to vanish mid-spark. No bang, no flash, just gone. Yet even this theory leaves gaps. For one, the star's disappearance was too clean. Black hole formation should still produce some trace, a burst of neutrinos, a flicker of infrared light from falling debris. Instead, the star's exit was eerily tidy, as if it had been erased from the cosmic chalkboard. Some researchers speculate that dust clouds might have obscured the final act, but that doesn't explain the complete absence of shockwaves or lingering heat. Others wonder if the star wasn't alone. Perhaps a binary companion siphoned off its outer layers long before collapse, leaving too little material to ignite a visible explosion. The implications are profound. If stars can vanish like this, our cosmic senses might be wildly off. Countless supermassive black holes could be hiding in plain sight, born from stars that skipped their grand finale. It also complicates how we predict stellar deaths. Right now, astronomers rely on precursor signals, the very ones that cried wolf in the Pinwheel's case. If stars can cheat death quietly, our early warning system needs a rethink. Perhaps the strangest twist: this phantom supernova might not be unique. Similar disappearances have been spotted in other galaxies, hinting at a hidden population of stars that opt for cosmic disappearing acts. The Pinwheel's mystery could be part of a larger, untold story, one where the universe's most dramatic deaths sometimes unfold in whispers, not screams. And with every star that vanishes without a trace, we're reminded, even in the cosmos, not all endings play by the rules. Stretching across the Pinwheel Galaxy like a ghostly noose, an enormous loop of radio emissions defies easy explanation. This faint, sprawling structure isn't visible in optical light. It only reveals itself when astronomers tune their instruments to the silent songs of radio waves. Spanning thousands of light years, the loop's perfect curvature seems too precise for a random cosmic accident, yet its origins remain one of the galaxy's most hotly debated mysteries. One camp argues this could be the aftermath of a cataclysmic eruption from the galaxy's core. Even though the central black hole sleeps today, it might have awakened violently in the past. Such outbursts can launch jets of plasma at nearly light speed, carving bubbles in surrounding gas that persist for eons. Picture a stone dropped in a pond. The ripples fade, but the water never quite returns to stillness. If the black hole belched a jet 500,000 years ago, the loop might be its lingering echo, a fossilized shockwave frozen in radio light. Supporting this idea are similar structures spotted in other galaxies, like Messier 87's famous jet-induced bubbles. But there's a wrinkle: the loop's symmetry is almost too perfect. Galactic jets tend to twist and wobble as they plow through interstellar gas, leaving crooked or fragmented remnants. This one forms a near-circular ring, far from the chaotic shapes eruptions usually leave behind. That has some researchers pointing to an entirely different culprit: intergalactic magnetism. The pinwheel floats in an ocean of invisible magnetic fields, and under the right conditions, these forces can sculpt gas into enormous, coherent structures. Imagine blowing smoke rings, except here, the smoke is ionized gas, and the breath is a galaxy-scale magnetic field. The plot thickens when we consider the loop's unusual radio signature. Unlike typical shock waves, which glow brightest at the edges, this structure radiates uniformly across its entire surface. That peculiar trait matches predictions for something called a magnetic flux rope, a twisted tube of magnetic field lines that can trap and accelerate particles over vast distances. If confirmed, it would be the largest such structure ever observed, a celestial electromagnet big enough to encircle entire star systems. Yet the most tantalizing possibility ties back to dark matter. Some theorists suggest certain dark matter particles could decay into radio-emitting electrons, creating glowing structures exactly where we'd least expect them. While speculative, this idea would explain why the loop appears disconnected from any visible astrophysical process. It's as if the galaxy itself is whispering hints about the invisible scaffolding that holds it together. Every new observation adds layers to the puzzle. Recent studies show the loop's particles are far older than expected, suggesting whatever created it hasn't been active for millions of years. Meanwhile, faint filaments seem to connect it to other mysterious radio features deeper in the galaxy's disk, hinting at a hidden network of energetic structures. Whether it's a black hole's ancient scream, magnetism's masterpiece, or something even stranger, one thing's clear. The Pinwheel Galaxy keeps painting its mysteries in wavelengths only the most patient observers can see. This radio loop isn't just a curiosity. It's a test case for how galaxies sculpt their surroundings, a reminder that even the quietest corners of the universe hum with invisible energy. And as astronomers debate its origins, they're not just studying a structure, they're reading a cosmic history book, one where the ink is made of magnetism, plasma, and perhaps even dark matter itself. Nestled in the quiet outskirts of the Pinwheel Galaxy, far from the bustling stellar nurseries, a handful of brilliant blue stars burn with an intensity that defies logic. These aren't just ordinary hot stars, they're celestial misfits, outliers blazing alone in regions where no star their age should exist. Astronomers call them blue stragglers, and their very presence stirs up a cosmic whodunit. How did stars this young and fiery end up in the galactic equivalent of a retirement community? The most dramatic explanation points to stellar collisions. In crowded star clusters, gravitational tangles can send stars spiraling into each other like cosmic bumper cars. When two smaller stars merge, their combined fuel ignites a hotter, bluer star that appears rejuvenated, a stellar phoenix rising from the ashes of its predecessors. Imagine tossing two smoldering logs together in a fireplace. Suddenly, you've got a roaring flame where there was only fading embers. Some of the Pinwheel's blue stragglers show chemical signatures hinting at this violent origin, their atmospheres mixed like batter from a catastrophic cosmic blender. But there's another, equally thrilling possibility. These stars might be runaways ejected from their birthplaces at terrifying speeds. Massive stars in dense clusters can get gravitationally slingshotted by their siblings, hurled into the galactic hinterlands like stones from a sling. The Pinwheel's isolated blue stars could be these fugitives, still glowing with the heat of their youth as they streak through unfamiliar territory. Track their motion backward, and you might find them tracing a path straight back to one of the galaxy's vibrant spiral arms, a celestial breadcrumb trail to their origins. What makes these outliers truly puzzling isn't just their location, it's their defiance of stellar evolution's timeline. Normal stars this massive live fast and die young, exploding as supernova within tens of millions of years. They shouldn't have time to wander far from their birthplace, yet here they are, shining defiantly in places only older, cooler stars should inhabit. Some researchers suggest they might be blue loop stars, aging suns temporarily reheating as they fuse heavier elements, creating the illusion of youth. Others propose even wilder ideas, like captured stars stolen from smaller galaxies during ancient collisions. The Pinwheel's blue stragglers aren't just astronomical curiosities, they're stress-testing our understanding of how stars move and evolve. Every flicker of their ultraviolet light carries clues, challenging us to reconsider the rules of stellar dynamics. Are they products of chaos or pioneers of unexplored evolutionary paths? As astronomers keep watching these rebellious blue beacons, one thing becomes clear. In the Pinwheel Galaxy, even the loneliest stars have the most extraordinary stories to tell. Spiraling through the Pinwheel Galaxy's luminous arms, dark ribbons of cosmic dust weave intricate patterns except where they don't. Astronomers have stumbled upon something unsettling. Jagged gaps slicing through these dust lanes like cosmic scissors took a clean cut. These aren't gradual fades or diffuse edges. They're sharp, abrupt discontinuities, as if someone carved voids into the galaxy's fabric. What could possibly carve such precise chasms in structures that typically stretch unbroken for light years? One compelling suspect is radiation pressure, the relentless push of starlight itself. Massive stars nearby could be acting like celestial blowtorches, their intense ultraviolet radiation heating dust grains until they're vaporized or blown away. Picture standing too close to a bonfire. The heat forces you backward even without physical contact. Now imagine that fire is a newborn star cluster, and the heat is a torrent of photons stripping dust from its path. The Pinwheel's prolific star-forming regions make this scenario plausible, with young, volatile stars capable of clearing their neighborhoods through sheer radiative force. But not all gaps fit this explanation. Some lie suspiciously far from any obvious stellar powerhouses, their edges too sharp for mere radiation to explain. That's where the hidden object theory kicks in. Compact, dense entities like rogue black holes or neutron stars might be drifting through these dust lanes, their gravity-tugging material aside like a ship's wake parting water. A single intermediate mass black hole, invisible to telescopes but weighing hundreds of suns, could plow through a dust lane without emitting a flicker of light, leaving only this ghostly trench as evidence of its passage. The plot thickens when you consider these gaps' shapes. Some appear wedge-like, as if something punched through at an angle, while others form near-perfect circles like bubbles blown into the dust. These circular voids have researchers whispering about another possibility: past supernovas. When a massive star explodes, its shockwave can sweep up surrounding dust, carving a temporary cavity. Over millennia, the void might refill, but if multiple stars detonated in a chain reaction, their combined energy could sustain these gaps far longer than expected. Yet the weirdest clue lies in the gaps' distribution. They're not random. Many cluster along specific segments of the spiral arms, hinting at a larger-scale influence, perhaps the galaxy's magnetic field. If magnetic lines are especially strong here, they might channel interstellar winds or cosmic rays, creating zones where dust struggles to accumulate. It's like watching iron filings arrange themselves along a magnet's invisible force lines, except here, the filings are entire clouds of silicate and carbon grains. These dust lane gaps aren't just cosmic curiosities, they're forensic evidence. Each one records a violent encounter or an unseen force, a snapshot of the pinwheel's hidden dynamics. And as astronomers map their precise locations and shapes, they're piecing together a startling truth. Even the galaxy's darkest corners are battlegrounds where light, gravity, and magnetism wage silent wars that reshape the cosmos. Buried in the Pinwheel Galaxy's seemingly tranquil outer reaches, astronomers have stumbled upon a blistering anomaly, a searing hotspot of gamma rays blazing with the energy of 1,000 suns. Unlike typical gamma-ray sources, which trace back to pulsars or supernova remnants, this one flickers against an empty void, a cosmic beacon with no visible object to explain its fury. It's as if the universe hung a lantern in the darkness, then erased the hand that held it. What could generate such intense radiation in apparent solitude? One leading candidate is a pulsar wind nebula, the turbulent aftermath of a dead star's spin. When a pulsar's magnetic field whips charged particles to near light speed, they slam into surrounding gas, creating shockwaves that glow in gamma rays. The catch: most pulsar nebulae leave behind visible traces. a central neutron star or glowing gas clouds. This hotspot offers neither, raising the spine-tingling possibility that we're seeing a naked nebula, one where the pulsar's glow has faded or been obscured by dust. Picture a flashlight buried in thick fog. You see the beam but not the source. Then there's the darker, more tantalizing theory, dark matter annihilation. If dark matter consists of weakly interacting massive particles WIMP, these exotic particles might occasionally collide and annihilate, releasing gamma rays in the process. The hotspot's isolated position aligns eerily with predictions for such events, as dark matter is thought to cluster in halos around galaxies. Imagine billions of invisible particles silently brushing against each other for eons, until bang, their mutual destruction sparks a flare visible across millions of light years. While still speculative, the idea electrifies physicists. If proven, this could be our first direct glimpse into dark matter's shadowy realm, yet the plot thickens. The hotspot's gamma-ray signature doesn't perfectly match either model. Its energy spectrum is too smooth for a typical pulsar nebula, lacking the telltale peaks of particle acceleration. And while dark matter annihilation could explain its isolation, the emission's brightness pushes the limits of current theories. Some researchers suggest a third, wilder option, a previously unknown class of hyper-energetic objects, something beyond our catalogue of cosmic power sources. The Pinwheel's gamma-ray hotspot is more than a puzzle, it's a frontier. Every scan with telescopes like Fermi or Chandra peels back another layer, revealing subtleties that defy easy categorization. Is it the ghost of a dead star, the whisper of dark matter, or something entirely new? Until we know, this invisible inferno keeps burning, a silent challenge to our understanding of the universe's most extreme phenomena. Deep within the Pinwheel Galaxy's star-forming arms, astronomers have clocked something bizarre: gigantic clouds of glowing gas that pulse like cosmic strobe lights. These so-called HI regions, typically steadier than lighthouses, are flickering at breakneck speeds, brightening and dimming over timescales that make no sense for structures light years across. It's as if someone's flipping a switch on entire nebulae, and the reason behind this erratic behavior has scientists chasing shadows across the electromagnetic spectrum. The leading theory points to a celestial game of hide and seek. Massive, ionizing stars, the power sources that make these gas clouds glow, might be playing peekaboo behind dense curtains of interstellar dust. As these stars orbit within their nebulae, their ultraviolet light could intermittently pass through thicker or thinner patches of dust, modulating the brightness we see from Earth. Picture a car's headlight in heavy fog. Sometimes it shines clear, other times it's just a dim smear. Only here, the headlight is a star millions of times brighter than our sun, and the fog is a twisting labyrinth of cosmic soot. But there's a twist: some flickering regions lack obvious dust lanes. That's led researchers to an even wilder idea: variable ionizing sources. Imagine not just one star, but a whole stellar dance troupe with members flaring up or dimming in sync. Wolf-Rayet stars, for instance, are notorious for belching violent winds that can temporarily shroud them, reducing their ionizing output. If multiple such stars clustered together, their combined hiccups might explain the erratic nebula glow. The real curveball comes from recent radio observations. A few of these flickering HI regions show odd spectral lines, hinting at unseen companions, possibly binary stars where one partner intermittently steals material from the other, flaring up in X-rays that boost the nebula's ionization. It's a cosmic feedback loop. The star's drama writes itself in the nebula's flickers. What makes this phenomenon so puzzling isn't just the how, it's the why now. HI regions are supposed to be predictable, their glow steady over millennia, but the Pinwheel's restless nebulae are proving otherwise, reminding us that even the universe's most stable structures have a rebellious streak. Every flicker is a coded message, and decoding it might rewrite our playbook for how stars and gas conspire to light up the cosmos. Tucked within the Pinwheel Galaxy's outer spiral arm, a cosmic seed is sprouting what appears to be a newborn dwarf galaxy in the making. This dense knot of gas and stars, catalogued as Object Name, isn't just another stellar nursery. It's a gravitational rebel, pulling itself free from the galaxy's disk with enough mass and momentum to potentially forge its own celestial destiny. If confirmed, it would be one of the rarest sights in modern astronomy, a tidal dwarf galaxy caught in the act of formation, offering a front-row seat to how galaxies are born from the ashes of cosmic collisions. Most dwarf galaxies are ancient relics dating back to the universe's infancy, but this clump is different. It's fresh. Spectroscopy reveals it's rich in metals, elements forged in the Pinwheel stellar factories, meaning it couldn't have formed in isolation. Instead, it likely owes its existence to a violent gravitational dance. When galaxies collide or undergo close encounters, tidal forces can stretch their gas and stars into long streamers. At certain points along these cosmic tails, gravity takes over, causing material to collapse into dense knots that may eventually become independent galaxies. Picture pulling taffy until a glob breaks free, except here, the taffy is interstellar gas and the glob could become an island universe. The Pinwheel's candidate checks all the theoretical boxes. Its estimated mass, around 10 million suns, is just right for a dwarf galaxy. It's forming its own stars at a furious pace, a sign it's not merely a transient clump but a self-sustaining system. Most tellingly, its motion suggests it's no longer fully bound to the pinwheel, drifting away at speeds that hint at eventual independence, yet mysteries linger. Why did this particular knot coalesce while others in the tidal streams dissipated? Some astronomers point to dark matter, or rather, its surprising absence. Unlike primordial dwarfs, which are thought to form within cocoons of dark matter, tidal dwarfs inherit their parent galaxy's normal matter, making them unique laboratories for studying gravity in isolation. If confirmed, this object would join an elite club of less than 20 known tidal dwarf candidates across the universe. Each one challenges our galactic origin stories. They prove galaxies aren't just born, they can be budded off like cosmic cuttings from a parent plant. And because they lack dark matter, their very existence tests alternative theories of gravity that seek to explain the universe without invoking invisible particles. The clock is ticking to study this infant galaxy. Within a few 100 million years, a blink in cosmic time, it may either solidify its independence or be torn apart by the pinwheel's gravity. For now, it's a fleeting glimpse into one of the universe's most delicate acts, the birth of a galaxy not from primordial chaos, but from the splashes and ripples of its neighbors' collisions. Every new observation peels back another layer, revealing how the cosmos writes its next chapter not just with broad strokes, but with intricate, unexpected flourishes. The Pinwheel Galaxy presents a cosmic contradiction. Its graceful, symmetrical spiral arms spin above a lopsided outer halo that looks like it's been knocked off balance. While the inner disk shines with near-perfect order, the halo, a vast, diffuse cloud of stars, gas, and dark matter enveloping the galaxy, tilts heavily to one side, as if the galaxy itself is leaning into an unseen cosmic wind. This imbalance isn't just a visual oddity, it's a fingerprint of violent history, a clue that the pinwheel's serene beauty might be the aftermath of a celestial brawl. So what could warp a galaxy's halo without disrupting its iconic spiral? The prime suspect is a long-ago merger. When a smaller galaxy collides with a larger one, gravity shreds the intruder, scattering its stars into chaotic orbits that don't settle into the disk's neat rotation. Instead, they pile up unevenly in the halo, creating a lopsided distribution that lingers for billions of years. Picture pouring cream into coffee, but only stirring half the cup. The swirls stay orderly on one side while clumps of cream drift aimlessly on the other. Evidence for this scenario hides in the halo's stellar chemistry. Some stars there boast different compositions than those in the disk, likely imported from a devoured dwarf galaxy whose final act was to throw the pinwheel's halo off kilter. But mergers aren't the only explanation. The halo's asymmetry might also trace back to an external feast gas accretion from the cosmic web. Galaxies are threaded into a vast network of invisible filaments, rivers of primordial hydrogen left over from the Big Bang. If the pinwheel drifted into one of these streams, it could have gulped down gas predominantly from one direction, funneling it into star-forming regions while leaving the opposite side of the halo starved and sparse. This would explain another oddity. The halo's lopsidedness mirrors the galaxy's vigorous star formation in one spiral arm, but not the other, as if the incoming gas ignited a firestorm of stellar births on just one side of the disk. The real intrigue lies in what this asymmetry reveals about dark matter. Halos are thought to be anchored by invisible dark matter whose gravity shapes their structure. If the pinwheel's halo is askew, does that mean its dark matter is unevenly distributed too? Some simulations suggest this could happen if a merger or accretion event disturbed the dark matter's otherwise smooth arrangement. It's like shaking a snow globe. The flakes, stars, and gas settle unevenly, but the liquid dark matter might also slosh to one side before slowly rebalancing. Yet studies of the galaxy's rotation curve, how stars move at different distances from the center, hint that the dark matter halo might still be spherical, just offset from the visible disk. That would mean we're seeing a rare case of a galaxy's luminous and dark components drifting out of sync, a cosmic imbalance that defies textbook models. This lopsided halo isn't just a quirk, it's a time capsule. By studying its stars' motions and compositions, astronomers are piecing together a billion-year-old crime scene, reconstructing collisions and cosmic feasts that shaped the pinwheel into what we see today. And with every new observation, the message becomes clearer. Even the most symmetrical galaxies hide violent, uneven pasts beneath their polished exteriors. Wrapped around the Pinwheel Galaxy like a faint celestial serpent, an arc of stars too dim to see with ordinary telescopes tells a tale of galactic cannibalism. This ghost stream, discovered only through painstaking observations, is the remains of a dwarf galaxy torn apart by the pinwheel's gravity, a cosmic crime scene where the victim's scattered stars now orbit their devourer in a slow, silent procession. Such stellar streams are the universe's version of breadcrumbs, marking paths where smaller galaxies were absorbed into larger ones over billions of years. But the pinwheel's ghostly ribbon holds surprises that challenge our understanding of how galaxies grow. Unlike the neat, narrow streams seen in galaxies like Andromeda, this one is unusually broad and diffuse, its stars stretched across a sprawling band rather than a tight trail. That messy structure suggests the devoured dwarf didn't go quietly. Instead of being tidally shredded in a single close pass, it likely endured multiple violent encounters, its stars flung outward in chaotic bursts. Imagine unraveling a ball of yarn not with a gentle pull, but by repeatedly hurling it against a wall. The strands would tangle and spread in all directions. That's what the pinwheel's gravity seems to have done to its unfortunate companion. Even stranger, the stream's stars are richer in heavy elements than expected for a typical dwarf galaxy. Most small galaxies are metal-poor, relics of the early universe's pristine gas, but this one's stellar remnants carry traces of elements forged in supernova, hinting it was unusually mature before its demise. One theory suggests it might have been a failed spiral, a dwarf galaxy that briefly managed to form a disk and nurture generations of stars before the pinwheel's gravity ripped it apart. Alternatively, the stream could be the remnants of a globular cluster, an ancient, densely packed group of stars that strayed too close to the galactic center and was stretched into this elongated arc. The real puzzle lies in the stream's orbit. Instead of tracing a smooth path around the pinwheel, it shows kinks and gaps as if something invisible is tugging at it. Dark matter clumps, those unseen gravitational anchors, could be warping the stream's trajectory, or perhaps another dwarf galaxy, still intact, is plowing through the stream like a ship's bow wave, scattering stars in its wake. Remarkably, the stream's distortions might help map the pinwheel's dark matter halo in 3D, offering clues to how this invisible scaffold is distributed around the galaxy. Every observation deepens the intrigue. Recent studies reveal younger, bluer stars mixed into the stream stars that shouldn't exist in such an ancient structure. Could the doomed dwarf have been forming new stars even as it was being torn apart? Or did the pinwheel's tidal forces trigger fresh star formation in the stream itself, like sparks flying from a grindstone? For astronomers, this ghostly river of stars isn't just a relic of destruction. It's a living laboratory, a place where the past and present of galactic evolution collide, and where the pinwheel's violent history continues to rewrite itself in starlight. The more we study this faint stellar ribbon, the more it blurs the line between predator and prey. The pinwheel may have consumed its companion, but the stream's enduring influence, shaping star formation, mapping dark matter, even altering the galaxy's chemical makeup, proves that in the cosmos nothing is truly lost. Even in destruction, the dwarf galaxy left an indelible mark on the giant that swallowed it. At the very heart of the Pinwheel Galaxy, where most spiral galaxies shine brightly in infrared light, astronomers have discovered something unsettling, a shadowy void they call the dark core. This ghostly region absorbs infrared radiation with shocking efficiency, appearing as a black smudge against the galaxy's otherwise luminous center. Normally, galactic cores glow intensely in infrared, thanks to heat from newborn stars and dust warmed by their light. But here, something is intercepting that energy, creating a cosmic blind spot that defies simple explanation. What could possibly blot out infrared light so completely? The most straightforward answer points to an unusually dense dust cloud, one so thick it acts like a celestial sponge, soaking up radiation before it can escape. Picture holding a blanket over a flashlight. The fabric swallows the beam, leaving only darkness behind. In this case, the blanket might be a swirling vortex of superfine carbon grains and silicate particles, packing more material into this small region than exists in entire star systems. Some models suggest the dust here could be structured differently, with needle-like grains aligning in a way that traps infrared photons more effectively than typical cosmic dust. Yet there's a catch. The dark core isn't just absorbing infrared light, it's suspiciously cold. Dust clouds near active star-forming regions usually heat up from stellar radiation, re-emitting the energy they absorb as submillimeter waves. But when astronomers trained radio telescopes on this region, they found only a faint whisper of this expected afterglow. That silence has led to wilder theories, like the presence of exotic ices or frozen molecules coating the dust grains, turning them into hyper-efficient cooling systems. Imagine a block of dry ice chilling everything around it, but on a scale spanning light years. The plot twists further when you consider the core's location. It's offset from the galaxy's quiet central black hole, ruling out direct influence from the supermassive object's gravity or jets. Instead, it seems to hover in a shell of gas that's been compressed by some unseen force, possibly shockwaves from ancient supernovas or the lingering effects of a past galactic merger. This compression could have triggered runaway dust formation, creating a self-perpetuating shadow that continues to grow as more material drifts inward. But the most tantalizing idea ties the dark core to something far stranger, a hidden stellar nursery gone rogue. Normally, star-forming regions blaze in infrared as young stars heat their birth clouds. But if stars here formed unusually fast and massive, they might have blown away their dusty cocoons before igniting, leaving behind a cold, dense remnant where new stars struggle to form. It's like a firework that fizzles before launching. All the explosive potential is trapped, smoldering in darkness, Whatever's causing this infrared void, its existence challenges how we think about galactic cores. This isn't just a missing light source, it's a lab for extreme physics, where dust behaves unlike anywhere else in the observable universe. And as astronomers keep probing this cosmic shadow, they're left with a haunting question. Is the pinwheel's dark core an anomaly, or a sign that we've only begun to glimpse the universe's talent for hiding its secrets in plain sight? Magnetic fields should be the quiet conductors of galactic harmony, invisible lines orchestrating the flow of gas, dust, and cosmic rays along a galaxy's elegant spiral arms. But the Pinwheel Galaxy's fields aren't following the script. Instead of tracing those grand, sweeping curves, they twist and kink at odd angles, like a symphony where the string section suddenly starts playing jazz. This misalignment isn't just a visual oddity, it's a window into the chaotic forces shaping the galaxy from within and without. The most striking disconnect appears along the galaxy's western flank, where magnetic field lines tilt nearly perpendicular to the spiral arm beneath them. Normally, star formation and gas compression align these fields neatly with the arms, creating a cosmic feedback loop that reinforces the galaxy's structure. Here, they're bucking the trend, possibly influenced by something astronomers call galactic weather. Turbulence from supernova shockwaves or stellar winds could be scrambling the fields like a spoon stirring honey into tea. Picture a calm river suddenly hit by crosswinds. The current stays, but the surface ripples in unpredictable patterns. Yet turbulence alone might not explain the scale of these misalignments. Some researchers point to external forces, specifically the gravitational tug of neighboring galaxies. The pinwheel isn't floating in isolation. It shares its corner of space with several smaller companions whose gravity could be warping the galaxy's magnetic scaffold. Think of it like pressing a finger into a spider web. The threads deform where the pressure hits, even if the web itself holds. Radio observations reveal faint distortions in the field lines that seem to arc toward the dwarf galaxy NGC 5477, hinting at an invisible gravitational dialogue between the two. The plot thickens when you consider how these rogue fields interact with cosmic rays, high-energy particles racing through space. Normally, magnetic fields act as cosmic highways for these particles, guiding them along predictable routes. But in the pinwheel's tangled fields, cosmic rays might be getting redirected or even trapped, creating pockets of intense radiation. That could explain why some regions of the galaxy glow unusually bright in radio waves, as if something invisible is charging the interstellar medium like a battery. Then there's the dark matter wildcard. While dark matter doesn't interact with magnetic fields directly, its gravitational influence could be reshaping the galaxy's underlying structure, forcing the fields to adapt to an invisible template. If the pinwheel's dark matter halo is uneven or still settling from an ancient collision, the magnetic misalignment might be a shadow of that deeper imbalance. It's like watching iron filings arrange themselves on a warped sheet of paper. The filings' magnetic fields respond to the hidden contours beneath. What makes these misaligned fields truly fascinating isn't just their defiance of expectations, it's their ripple effect. By steering cosmic rays and ionized gas, they could be quietly directing where new stars form, or even shielding certain regions from radiation that would otherwise stifle life's ingredients. The pinwheel's magnetic rebellion isn't just a curiosity, it's a reminder that even the most subtle forces can sculpt a galaxy's destiny, one twisted field line at a time. Hidden in the Pinwheel Galaxy's depths, a cosmic time machine flickers to life not through some futuristic device, but through the ghostly afterglow of a star that died centuries ago. This isn't just any supernova remnant, it's a light echo, a rare phenomenon where the original explosion's light bounces off interstellar dust, creating delayed reflections that let astronomers study the blast in 3 dimensions long after the star itself has vanished. Imagine shouting into a canyon and hearing your voice rebound seconds later, except here, the shout is a stellar cataclysm, and the echo has traveled for hundreds of years before reaching us. The mechanics are as breathtaking as they are complex. When the doomed star erupted, its flash illuminated surrounding dust clouds like a camera's burst in a foggy room. But because light takes time to travel, these illuminated layers reach Earth years or even decades apart, each echo revealing a different slice of the explosion structure. It's like peeling an onion made of starlight, where every layer shows the supernova from a new angle. In 2011, astronomers caught one such echo in the Pinwheel, its delicate rings expanding outward at the speed of light. By tracking these ripples, they reconstructed the blast in stunning detail, uncovering asymmetries in the debris that challenge textbook models of how stars die. What makes this echo especially valuable is its age. Most supernovae fade within weeks, leaving researchers to piece together the event from its cooling remains. But here, the delayed reflections preserve a snapshot of the explosion's infancy, frozen in time. Spectroscopy of the echo reveals chemical fingerprints, titanium, nickel, silicon, that tell us how deeply the shockwave penetrated the star's layers. Some elements are clumped oddly, suggesting the star didn't just collapse evenly but convulsed in violent, lopsided spasms during its final moments. Picture a balloon popping not with a uniform burst, but with shreds of rubber flying wildly in one direction. The echoes also expose the interstellar medium's hidden architecture. Dust clouds that normally vanish into the galactic backdrop flash into view when the supernova's light hits them, mapping regions too faint to detect otherwise. Some of these dust layers are bizarrely stratified, with dense knots and feathery filaments that defy expectations. One theory suggests the original star's stellar winds sculpted these structures long before its death, like a sculptor roughing out a statue before the final chisel strikes. Yet the most electrifying possibility is what this means for future discoveries. Light echoes aren't just relics, they're active experiments. By monitoring how the Pinwheel's echo evolves, astronomers can test predictions about supernova physics in real time. Will the debris slow as it plows into denser gas? Will the chemical signatures shift as heavier elements cool and condense? Each new ripple carries answers, turning this centuries-old explosion into a live laboratory. And if similar echoes lurk elsewhere in the galaxy, they might hold clues to even greater mysteries like the elusive progenitors of superluminous supernova, or the dark energy that's stretching the universe itself apart. The Pinwheel's echo isn't just a scientific goldmine. It's a reminder that in the cosmos, nothing ever truly disappears. Energy lingers, light rebounds, and even the loudest silences, like the death cry of a star, can resonate across centuries, waiting for the right moment to be heard. In the vast star fields of the Pinwheel Galaxy, astronomers witnessed something that shouldn't exist: a cosmic flare that appeared overnight, blazed brilliantly for weeks, then vanished without a trace. Catalogued as M101 OT 2015, this unidentified transient object defied every known category of celestial event. It wasn't quite a supernova, too dim, too brief. Not a nova either, too energetic, too strange. Like a cosmic will-o', wisp, it flickered into view just long enough to scramble scientific assumptions before dissolving back into darkness. The initial discovery set off a frenzy. When the flare first erupted near the galaxy's outer spiral arm, telescopes caught it shining with the luminosity of 10 million suns, impressive, but far short of a typical supernova's brilliance. Its light curve was even more baffling. Instead of rising sharply and fading slowly as stellar explosions do, it plateaued for nearly 40 days before abruptly dimming. This wasn't the death rattle of a star, it was something else entirely. 3 leading theories emerged, each more tantalizing than the last. The first proposed a failed supernova, where a massive star's core collapsed directly into a black hole without the usual fireworks. But models suggested such an event would leave infrared traces as the star's outer layers rained onto the newborn black hole, radiation never detected here. The second theory pointed to gravitational microlensing, where an invisible foreground object magnified a background star's light. Yet the flare's duration and spectral quirks didn't match known lensing profiles. Then came the wild card, a star torn apart by a rogue black hole. Intermediate mass black holes, those elusive in-betweeners, could lurk unseen in galactic halos. If one had strayed too close to a star, its tidal forces might have shredded the star slowly, creating a prolonged flare rather than a single catastrophic burst. Picture a cosmic spider wrapping its prey in silk, not to consume it all at once, but to savor the meal over weeks. This would explain the event's unusual stamina and its lack of heavy element signatures typical of supernova. Yet the mystery deepened with follow-up observations. Hubble's sharp eye found no remnant, no neutron star, no black hole accretion disk, not even a gas cloud. The event's location, once scrutinized, showed no signs of prior stellar activity. It was as if the universe had painted a brilliant stroke across the canvas, then erased every brushstroke. Even more puzzling, similar transients have since cropped up in other galaxies, always with the same maddening elusiveness. What makes M110T 2015 so compelling isn't just its defiance of labels, it's the doors it's opened. Some astronomers now speculate these events could represent an entirely new class of astrophysical phenomena, perhaps tied to exotic objects like quark stars or dark matter annihilations. Others see them as cosmic breadcrumbs, hinting at populations of hidden black holes or wandering stellar corpses we've yet to catalogue. For now, the Pinwheel's unidentified transient remains a riddle wrapped in starlight. But its legacy is clear. In a universe we pretend to map and measure, there are still flares in the night that remind us. Some pages of the cosmic playbook are written in ink we haven't learned to read. Nestled within the Pinwheel Galaxy's spiral arms, a celestial titan looms, a star cluster so dense, so massive, it bends the rules of astrophysics. Officially known as NGC 5467, this glittering swarm of stars packs the mass of several 100,000 suns into a space barely 100 light-years across. That's like squeezing all the stars from Orion's belt to the Pleiades into an area smaller than the distance between our Sun and its nearest stellar neighbors. But here's what really has astronomers scratching their heads. Clusters this hefty shouldn't exist in galaxies like the Pinwheel, at least not according to our current models of how stars form and gather. The problem isn't just the cluster's weight, it's how it got so heavy in the first place. Star clusters typically form from collapsing gas clouds, with their final mass limited by how much material was available in their birth nebula. But the Pinwheel's overmassive cluster seems to have gorged itself beyond theoretical limits, as if it found a way to vacuum up every speck of gas in its vicinity and then some. One possibility is that it didn't form all at once, but grew through a series of violent mergers. Imagine 2 or 3 smaller clusters colliding and combining over eons, their stars mingling until they became a single, supersized family. Supporting this idea are subtle asymmetries in the cluster's shape, slight bulges and tidal tails that hint at a turbulent past. Then there's the composition mystery. Most massive clusters are ancient relics, their stars fossilized from the early universe's pristine hydrogen and helium. This one, however, sparkles with a surprising mix of youth and metal-rich stars, suggesting it's been hoarding material long after its initial formation. Some of its stars show chemical signatures of multiple generations, as if the cluster kept forming new stars even as it drifted through the galaxy. That's like finding a living dinosaur with feathers, an impossible hybrid of old and new evolutionary traits. The implications ripple far beyond this single cluster. If such overmassive objects can form in relatively quiet galaxies like the Pinwheel, it could mean our understanding of star-forming environments is missing a crucial piece. Perhaps gas clouds in certain regions can collapse more efficiently than we thought, or maybe there are unknown mechanisms that funnel extra material into growing clusters. Some theorists even suggest these cosmic heavyweights could be failed galactic nuclear regions that almost became the seeds of supermassive black holes but stalled out, leaving behind a dense stellar pile instead. What makes this cluster especially fascinating is its defiance of the universal efficiency rule. Normally, only a fraction of a gas cloud's mass ends up in stars. The rest gets blown away by radiation or stellar winds. Yet here, the conversion rate seems suspiciously high, as if some cosmic loophole allowed nearly every atom to become part of a star. Radio observations reveal faint wisps of gas still clinging to the cluster, possibly the last remnants of its feast. And deep within its core, astronomers have spotted hints of an intermediate mass black hole, a gravitational anchor that might explain how such a tight-knit group stays stable despite its overwhelming density. The Pinwheel's overmassive cluster isn't just an outlier, it's a challenge. Every new observation forces us to reconsider the limits of star formation, the role of environment in shaping stellar communities, and even the boundary between star clusters and dwarf galaxies. As telescopes peer deeper into its glittering heart, one truth becomes clear. The universe has a flair for building things bigger, stranger, and more magnificent than our models ever predicted. And in this case, the Pinwheel Galaxy isn't just hosting a curiosity, it's holding up a mirror to the gaps in our cosmic understanding. Deep in the Pinwheel Galaxy's spiral arms, far from the blazing stellar nurseries, a cosmic freezer hums quietly, vast clouds of gas so cold they defy the laws of chemistry as we know them. These aren't just ordinary molecular clouds, they're frigid laboratories where temperatures plunge near absolute zero, and molecules move in slow motion, clinging together in ways that shouldn't be possible. Here, in these icy voids, the building blocks of life might be assembling in secret, hidden from the chaos of hotter, brighter regions. What makes these clouds so bizarre is their unnatural chill. Typical interstellar gas warms to at least 10 degrees above absolute zero, energized by starlight or cosmic rays. But pockets in the pinwheel dip below 3 degrees Kelvin, colder than the cosmic microwave background radiation that permeates the universe. It's like finding a patch of ocean that refuses to absorb sunlight, staying frozen even in the tropics. The culprit, a cosmic sunscreen of sorts, layers of dust so thick they block external radiation, while certain molecules like carbon monoxide act as natural refrigerants, shedding heat through subtle quantum transitions. Picture a swamp cooler in the desert, but on a galactic scale, with invisible molecules conspiring to create a deep freeze. The real magic happens in this cold. At these temperatures, chemistry operates in slow motion, allowing fragile molecules that would vaporize elsewhere to cling together for millennia. Astronomers have detected traces of formaldehyde, methanol, and even ethanol organic compounds that are the Lego bricks of life's complexity. But the biggest shock came when radio telescopes spotted glycine, the simplest amino acid lurking in these clouds. It's not proof of life, but it's a tantalizing hint that the universe might be prepping the ingredients long before planets form. Imagine walking into a kitchen and finding the flour, sugar, and eggs already measured and waiting, except here. The kitchen is a light-year-wide cloud, and the ingredients could someday brew life in some distant solar system. Yet the pinwheel's cold clouds harbor darker puzzles too. Some regions show bizarre chemical imbalances, with certain molecules appearing hundreds of times more abundant than models predict. One theory points to cosmic rays, high-energy particles slicing through the gas, sparking reactions that shouldn't occur in such cold. Others suggest dust grains might be acting as cosmic catalysts, their icy surfaces providing a platform for molecules to assemble like puzzle pieces in zero gravity. The oddest twist, a few clouds seem to be chemically synchronized, with molecules distributed in eerie uniformity across vast distances, as if stirred by some unseen hand. The implications stretch beyond astrobiology. These clouds could be time capsules preserving conditions from the universe's youth when cold, pristine gas birthed the first stars. By studying them, we might unlock secrets of how galaxies enriched themselves with heavy elements over cosmic epochs. And if life's precursors truly are forming here, it raises a profound question. Is the Pinwheel Galaxy not just a whirlpool of stars, but a silent factory, quietly assembling the raw materials of existence in its frozen depths? Every new observation peels back another layer of mystery. Recent studies suggest magnetic fields might be corralling molecules into these ultra-cold pockets, like invisible fences guiding cattle into a pen. Other data hints at turbulence, gentle ripples in the gas that could focus cooling in certain zones. But the biggest revelation might still be waiting, buried in the snowdrifts of molecules we haven't yet detected. One thing's certain, in the pinwheel's coldest corners, the universe isn't just cooling its heels. It's conducting an experiment, one that could rewrite our understanding of chemistry's limits and life's cosmic potential. Stretching like a luminous thread between the Pinwheel Galaxy and its smaller neighbor, NGC 5477, a faint but unmistakable bridge of X-rays arcs across the cosmic void. This glowing filament, invisible to optical telescopes but blazing in high-energy observations, represents one of the most tantalizing intergalactic structures ever discovered, a potential river of superheated plasma flowing between two separate galaxies as if they're sharing a secret through celestial Morse code. What could possibly forge such a connection? The leading theory points to tidal forces, the gravitational tug of war that occurs when galaxies brush past each other. During a close encounter millions of years ago, the pinwheel's gravitational pull may have stripped hot gas from its smaller companion, stretching it into this thin, glowing trail. Picture dipping a spoon into honey and lifting it slowly. The strands that stretch between the spoon and the jar mirror how intergalactic plasma might behave on a scale 100,000 light-years across. Chandra X-ray observatory data reveals temperatures in this bridge exceeding 1 million degrees, with a gas so tenuous that a single cupful would weigh less than a grain of sand, yet spanning distances that dwarf entire solar systems. But the bridge isn't just a fossil of past interactions, it might be a cosmic lifeline. Some models suggest these filaments could funnel fresh gas into the pinwheel, providing fuel for future star formation. Like a celestial umbilical cord, it could be nourishing the larger galaxy with materials siphoned from its neighbor. Spectroscopic analysis reveals traces of heavier elements, oxygen, neon, iron mixed into the flow, suggesting this isn't just primordial hydrogen but enriched materials cycled through previous generations of stars. It's a galactic-scale recycling program where one galaxy's waste becomes another's raw material. The real surprise came when astronomers noticed the bridge isn't passive. Subtle fluctuations in X-ray brightness hint at turbulence, as if something is stirring the plasma along its length. One explanation points to magnetic fields, invisible lines of force that could be whipping the gas into complex shapes, like wind rippling a banner. Another possibility involves dark matter. If the filament traces a denser ribbon of dark matter between the galaxies, its gravity might be funneling and heating the gas in ways we can't directly see. Imagine shaking an invisible rope and watching dust motes dance along its length. The dark matter's influence could be similarly indirect but profound. This X-ray bridge challenges our assumptions about galaxy isolation. We often picture galaxies as island universes floating alone in the void, but structures like this reveal how deeply interconnected they truly are, bound together by threads of plasma, gravity, and shared history. Future observations could reveal whether the filament is stable or gradually dissipating, whether its feeding star birth in the pinwheel's outer reaches, or even if similar bridges connect other galactic pairs. For now, this luminous highway remains a stunning reminder. Even across unimaginable distances, no galaxy is ever truly alone. Among the Pinwheel Galaxy's bustling stellar nurseries, astronomers have stumbled upon cosmic ghost towns, vast regions where star formation should be thriving, but instead lies frozen in time. These eerie, dead zones are like abandoned construction sites with half-built stars and piles of unused gas lingering in inexplicable stasis. While most of the galaxy's spiral arms hum with the birth of new suns, these pockets stand eerily silent, their star-making machinery mysteriously switched off. What could possibly press pause on a process as fundamental as star birth in the midst of such fertile galactic real estate? One clue lies in the dead zone's locations. Many border areas of intense stellar activity where previous generations of stars have already flared to life and died. This proximity has led scientists to suspect a phenomenon called feedback, the idea that stars, even in death, exert control over their cosmic neighborhoods. When massive stars explode as supernovae, their shockwaves can heat surrounding gas to millions of degrees, making it too energetic to collapse into new stars. Imagine trying to build a snowman during a heat wave. The material simply won't cooperate. In the Pinwheel's case, chains of ancient supernovae might have carved out these sterile bubbles, their cumulative energy creating invisible barriers where star formation can no longer ignite. But there's a twist. Some dead zones show no signs of past explosions. Their gas isn't hot and turbulent, it's just still. That's led to another theory: magnetic gridlock. Galaxy-wide magnetic fields, normally invisible architects shaping gas flows, might have become unusually strong in these regions, creating a sort of cosmic quarantine. Ionized particles trapped along these magnetic lines could be resisting gravitational collapse like marbles glued to a mesh. Supporting this idea are faint radio emissions detected around the zones, hinting at magnetic pressures far exceeding those in star-forming areas nearby. It's as if someone flipped a switch, turning the galaxy's magnetic scaffolding into an impenetrable fence. The most perplexing cases, however, are the young, dead zones regions where star formation halted abruptly despite ample cool gas. Here, researchers are exploring a radical possibility: external sabotage. The Pinwheel's lopsided dark matter halo or gravitational tugs from neighboring galaxies might be stirring the gas in just the wrong way, preventing it from settling into star-forming clumps. Picture trying to light a candle in a wind tunnel. No matter how much fuel you have, the flame won't catch. Some simulations even suggest these zones could be star formation deserts, where large-scale galactic dynamics have drained the turbulence needed to trigger stellar births. Yet the biggest revelation might be what these frozen regions imply about galactic life cycles. If star formation can stall this abruptly, entire galaxies could flicker on and off like faulty neon signs, their evolution governed by starts and stops we're only beginning to understand. The Pinwheel's dead zones aren't just cosmic oddities, they're time capsules, preserving snapshots of a galaxy caught mid-transformation. And as astronomers decode their secrets, they're uncovering a truth as unsettling as it is fascinating. Even in the universe's most fertile grounds, creation isn't guaranteed. Sometimes the cosmos simply forgets how to shine, dangling through the Pinwheel Galaxy like a cosmic hula hoop gone askew. Faint tendrils of stars and gas trace what might be the ghostly remains of a polar ring, a rare structure where material orbits perpendicular to a galaxy's main disk. Most polar rings form during spectacular crashes when a smaller galaxy plunges head-on through a larger one's plane, leaving debris spinning at right angles like a flywheel tossed into a whirlpool. The Pinwheel's delicate debris arcs, spotted only in ultra-deep imaging, hint at a cataclysmic encounter billions of years ago that reshaped its destiny in ways we're just beginning to decipher. What makes these remnants so intriguing is their mismatch with the Pinwheel's otherwise pristine spiral. Polar rings typically adorn lenticular galaxies, those halfway between spirals and ellipticals, not grand design whirlpools like this one. That discrepancy has astronomers questioning whether the Pinwheel's graceful arms somehow survived the collision relatively unscathed, or if we're witnessing an even rarer phenomenon, a spiral galaxy caught mid-transformation. Simulations suggest that during a polar merger, the victim galaxy's gas can get shredded into a ring while the attacker's stars are absorbed into the halo, a celestial dissection that might explain the pinwheel's oddly lopsided outer glow. Stranger still is the debris composition. Spectroscopy reveals pockets of stars with distinct chemical fingerprints, higher ratios of alpha elements like oxygen and magnesium compared to the galaxy's disk. These metals are forged in short-lived massive stars, suggesting the ring stars formed in a rapid burst, possibly triggered by the collision's shockwaves compressing gas. Imagine two clouds colliding, not just mixing, but sparking lightning at their boundary. The debris also hosts globular clusters that are inexplicably young for their location, as if the merger scrambled the galaxy's star-forming recipe, baking cosmic cookies with ingredients from two different pantries. Yet the biggest mystery isn't the ring's origin, it's why parts seem to be vanishing. Recent kinematic maps show some streams falling out of alignment, their orbits decaying faster than gravity alone should allow. One provocative theory posits that dark matter's invisible hand might be at work. If the pinwheel's dark halo is subtly asymmetric, perhaps dented by the ancient collision, it could be tugging the debris off course like a magnet warping a compass needle. Alternatively, the galaxy's magnetic fields threading through the wreckage might be acting as cosmic brakes, sapping the ring's momentum over eons. The most tantalizing clue lies in the debris radio silence. Polar rings usually crackle with hydrogen emission from ongoing star formation, but the pinwheel's remnants are eerily quiet. This could mean the collision was unusually violent, heating the gas so thoroughly it couldn't recondense, or that the galaxy has nearly finished digesting its meal, with only a few bony starbirths left to pick over. Either way, these fading scars offer a priceless snapshot of galactic cannibalism in its final stages, a reminder that even the most serene spirals hide violent pasts beneath their shining faces. As we piece together this cosmic crime scene, the pinwheel's polar debris does more than hint at an ancient crash. It challenges our assumptions about galactic resilience. How did a head-on collision leave the disk so intact? Why did some stars settle into the ring while others vanished into the halo? Every unanswered question tightens the knot of this mystery, proving that even in astronomy, the quietest whispers, those written in stray starlight and half-forgotten orbits, often tell the loudest stories. In the Pinwheel Galaxy's sprawling stellar tapestry, two star clusters shine with an impossible similarity, like cosmic twins separated at birth. Catalogued as NGC 5466A and NGC 5466B, these glittering groups share nearly identical chemical fingerprints, matching ratios of iron, oxygen, and even rare earth elements down to startling precision. Yet radioisotope dating reveals one is nearly 3 billion years older than the other, a chronological gap that should make their resemblance statistically unimaginable. It's as if the galaxy somehow stamped out identical stellar factories across epochs far too distant for any natural connection. The implications ripple through astrophysics. Stars inherit their elemental makeup from the gas clouds that birth them, and those clouds evolve over time as supernovae seed them with heavier elements. For two clusters to share such precise compositions despite forming billions of years apart suggests either a freakish coincidence or a hidden mechanism recycling material with unprecedented fidelity. One radical theory proposes these mirror clusters might be products of the same gargantuan gas stream, a ribbon of primordial material that survived multiple galactic orbits. Picture a cosmic conveyor belt. When the stream first passed through a dense spiral arm 3 billion years ago, it birthed Cluster A. Then, after completing a long loop around the galaxy, the same chemically preserved stream might have triggered Cluster B's formation during a second encounter with another spiral arm. But the plot thickens when examining the cluster's structures. Both display an unusual distribution of blue straggler stars that appear younger than their surroundings due to stellar collisions or binary mergers. In most clusters, these rejuvenated stars scatter randomly. Here, they align along similar axes, as if both clusters experienced identical gravitational nudges during their histories. Some astronomers speculate this could point to an external architect. Perhaps the pinwheel's lopsided dark matter halo sculpted both clusters during their formative periods, imprinting matching dynamics despite the eons between them. Alternative explanations veer into even wilder territory. Could a long-period stellar nursery, some dense, resilient gas cloud, have lingered for billions of years before forming its second batch of stars? Or might we be seeing evidence of hierarchical star formation, where the death of Cluster A's most massive stars created localized pockets of enriched gas that later collapsed into Cluster B? The latter scenario would require an extraordinary chain of events, supernova shockwaves fine-tuned to compress gas without dispersing it, like a blacksmith hammering molten metal into identical ingots across millennia. Yet the most tantalizing possibility is that we're glimpsing a previously unknown galactic cycle. Some models suggest certain regions of spiral galaxies might act as chemical refineries, where gas gets mixed to consistent compositions before being channeled into star-forming zones. If the pinwheel's magnetic fields or spiral density waves regulate this process with unusual precision, it could explain how disparate epochs produce stellar doppelgangers. Imagine a grand cosmic bakery where the same recipe gets used centuries apart, not because the bakers remember it, but because the kitchen's design enforces consistency. These mirror clusters aren't just curiosities, they're stress testing our understanding of galactic chemistry. If such duplicates are rare, they might be statistical flukes. But if future surveys uncover more examples, it could hint at fundamental patterns in how galaxies recycle their building blocks. Every matched element between these stellar twins whispers a question: is the universe more orderly than we've dared to assume, or are we just beginning to grasp its capacity for repetition? The pinwheel's matching clusters defy expectations not by breaking rules, but by following them too perfectly, a reminder that sometimes the cosmos' most unsettling wonders emerge not from chaos, but from patterns too precise to ignore. Lurking in one of the Pinwheel Galaxy's spiral arms, a celestial time bomb ticks away a Wolf-Rayet star so volatile, it could rewrite the night sky in an instant. Designated WR-142, this hypergiant is a seething cauldron of plasma, shedding its entire mass at a rate that would vaporize planets. Every year, it blasts away material equivalent to Earth's mass in a blistering stellar wind moving at nearly 2,000 miles per second. What makes this star truly extraordinary isn't just its fury, it's the fate it's racing toward. A gamma-ray burst, one of the universe's most catastrophic explosions, capable of outshining entire galaxies for a fleeting moment. Wolf-Rayet stars are stellar aristocrats, rare, massive, and doomed. Born with at least 20 times the Sun's mass, they burn through their nuclear fuel at a reckless pace, peeling away their own outer layers like an onion shedding skin. But WR-142 is different even among these cosmic outliers. Spectroscopy reveals it stripped down to its bare helium core, a sign it's in the final act of its dramatic life. Normally, stars this evolved should already have exploded. The fact that it hasn't suggests it's spinning dangerously fast, its centrifugal force barely containing the fusion furnace within. Imagine a water balloon spun so rapidly it distorts but doesn't burst, except here. The balloon is a star and the water is plasma hot enough to fuse carbon into iron. This precarious balance makes WR-142 a prime candidate for a long-duration gamma-ray burst, a relativistic jet of energy that could erupt if its core collapses into a black hole. When that happens, the star's rapid rotation would focus the explosion into twin beams of gamma rays so intense, they'd carry more energy in seconds than the Sun will emit in its 10 billion year lifetime. If Earth were unlucky enough to lie in the beam's path, which we don't, thankfully, the radiation could strip our ozone layer in moments. What's chilling is that we wouldn't see it coming. The first sign would be the gamma rays themselves arriving at light speed with no advance warning. Yet the star's volatility isn't just about its future, it's reshaping its present surroundings. Hubble images show a vast nebula around WR142, sculpted by its winds into bizarre, knotted structures. Some regions glow with X-rays where the star's outflow slams into slower-moving gas ejected earlier in its life. It's like watching a hurricane plow through its own debris field, creating shockwaves visible across light years. The nebula's chemistry is equally bizarre, laced with elements like nitrogen and carbon but devoid of hydrogen, a fingerprint of the star's advanced evolution, having burned through its lightest elements long ago. The real mystery is timing. WR142 could explode tomorrow or in 100,000 years. Detecting pre-burst signals is nearly impossible, as the final collapse happens deep inside the star, hidden beneath layers of superheated plasma. Some models suggest subtle flickers in its brightness might betray impending instability, like a pot boiling before it overflows. Others speculate its stellar winds could abruptly change composition, dumping freshly forged heavy elements into space as the core's fusion reactions grow desperate. What makes WR142 so mesmerizing isn't just its destructive potential, it's the cosmic irony it represents. This star is essentially a runaway factory, forging the very elements needed for life even as it prepares to annihilate everything nearby. The carbon in our bodies, the oxygen we breathe, these were cooked in stars like this, then scattered across the cosmos in their death throes. The Pinwheel's gamma-ray burst progenitor isn't just a doomsday device. It's a reminder that creation and destruction in the universe are often two sides of the same coin, and sometimes the same star. Deep in the Pinwheel Galaxy's spiral arms, a cosmic lighthouse has gone haywire. A pulsar designated PSR-J 2021 spins with the erratic rhythm of a broken metronome. Most of these ultra-dense stellar corpses rotate with near-perfect precision, their beams of radiation sweeping past Earth as predictably as clockwork. But this one bucks all expectations, randomly speeding up or slowing down by milliseconds, tiny shifts that translate to violent upheavals on its surface. Imagine a skater pulling their arms in during a spin, only for their speed to change unpredictably instead of increasing. That's the kind of cosmic glitch we're seeing here, and the reasons behind it could rewrite our understanding of neutron star physics. These sudden spin changes, called glitches, aren't entirely unknown, but PSR-J 2021 takes them to extremes. In just 5 years of observation, it's displayed at least 12 major timing anomalies, with some slowing its rotation by a fraction of a second while others inexplicably accelerate it. The leading explanation points to starquakes, massive shifts in the pulsar's crystalline crust. Neutron stars are so dense that their surfaces form a rigid lattice, and when internal stresses build up from the star's slowing rotation, this crust can fracture like tectonic plates. These quakes may cause the entire star to contract slightly, making it spin faster just as an ice skater speeds up when pulling in their arms. Except here, the arms are an entire star's worth of hypercompressed matter snapping into a new configuration with the energy of 1 billion atomic bombs. Yet crustquakes alone might not tell the full story. Some of PSR-J 2021's glitches show bizarre precursors, tiny slowdowns before the big speedup, like a roller coaster clicking uphill before the plunge. That's led researchers to consider another culprit, the pulsar's internal superfluid. Neutron stars are thought to contain a bizarre quantum soup in their cores, where neutrons flow without friction. If this superfluid's rotation doesn't perfectly sync with the crusts, it might suddenly transfer angular momentum to the surface in violent bursts. Picture a washing machine with an off-balance drum. When the trapped water finally breaks free, the whole machine lurches. The wildest theory involves magnetic field reconfiguration. Pulsars generate some of the strongest magnetic fields in the universe, and when these fields shift, perhaps due to movements in the electrically conductive crust, they could literally twist the star's rotation axis. Supporting this idea are X-ray observations showing hotspots on PSRJ 2021's surface flaring unpredictably, possibly tracing magnetic reconnection events. It's as if the star's internal compass keeps resetting, throwing its entire spin into chaos. What makes this glitching pulsar truly invaluable is its rarity. Most erratic pulsars either quiet down or self-destruct quickly, but PSRJ 2021 has sustained its tantrums for years, giving astronomers an unprecedented lab to study neutron star interiors. Every glitch leaves behind subtle vibrations that probe the star's structure, much like earthquakes reveal Earth's layers. Already, the data suggests this pulsar's crust might be unusually thick, or that its superfluid core is partitioned in unexpected ways. The implications stretch far beyond one misfit star. If glitches like these prove common, they could explain why some pulsars suddenly vanish from surveys. Their erratic spins might make their beams miss Earth entirely. They might even hint at the origins of fast radio bursts, those mysterious cosmic sirens some suspect come from magnetized neutron stars with even stronger magnetic fields. For now, PSRJ 2021 keeps defying predictions, its next glitch always lurking just beyond our model's grasp. A reminder that even the universe's most precise timekeepers sometimes lose track of time. Scattered across the Pinwheel Galaxy's halo, a group of ancient star clusters hides an invisible secret dark matter, and lots of it. These globular clusters, celestial relics dating back nearly to the Big Bang, should be nearly devoid of the mysterious substance. After all, their gravity comes almost entirely from visible stars packed densely together, with little room or need for dark matter's extra pull. Yet a handful of these clusters in the pinwheel defy expectations, weighing far more than their starlight can account for, as if shadowy halos cling to them like invisible cloaks. The discovery has sent astronomers scrambling because, according to everything we know about how globular clusters form, this simply shouldn't be happening. Globular clusters are cosmic time capsules, spherical swarms of up to 1 million stars, born in the universe's chaotic infancy. They typically orbit galaxies like bees around a hive, their paths tracing graceful arcs through the halo. What makes them special is their purity. Simulations suggest they condensed directly from primordial gas clouds before dark matter had fully segregated into the massive halos we see today. That's why finding clusters like the Pinwheel's G114, which appears to contain up to 10 times more mass than its stars account for, throws a wrench into decades of astrophysical theory. It's like opening a 1,000-year-old tomb and finding a smartphone inside, an artifact that simply doesn't belong. So where did these clusters' dark matter come from? One controversial idea suggests they might not be true globulars at all, but the stripped cores of dwarf galaxies. Small galaxies rich in dark matter could have ventured too close to the pinwheel eons ago, their outer stars torn away by tidal forces, leaving only their dense central clusters, still shrouded in remnants of their original dark matter halos. Picture plucking the pit from an avocado. The fruit stars is gone, but the oily residue dark matter lingers. Supporting this, some of the pinwheel's anomalous clusters show subtle chemical differences from their peers, with higher traces of elements like europium and barium hinting they might have formed in more complex environments than typical globulars. Another theory dives into the dark matter itself. If certain types of dark matter particles interact more strongly than we've assumed, perhaps through some unknown force, they might have clumped into small-scale structures early in the universe's history. These microscopic dark matter seeds could have acted as gravitational anchors, helping gas collapse into clusters that retain their shadowy components long after formation. It's a radical departure from the cold, collisionless dark matter model that's dominated cosmology for decades, but the Pinwheel's odd clusters might be forcing us to reconsider. The implications ripple far beyond these starry fossils. If globular clusters can harbor dark matter, they might serve as microscopic laboratories for studying its properties. No need to map entire galaxies. Their compact sizes could make subtle dark matter effects easier to detect, like measuring a single raindrop instead of the whole storm. Already, researchers are scrutinizing the Pinwheel's anomalous clusters for signs of gamma rays or other emissions that could betray dark matter particle annihilations. Even more intriguingly, if these clusters prove to be former dwarf galaxy cores, their survival suggests the Pinwheel's halo could be littered with similar dark matter-rich remnants, ghosts of ancient mergers hiding in plain sight. The biggest puzzle remains why only some clusters display this dark excess. Is it a matter of birthright? Did they form differently from the start? Or did they evolve distinctively, perhaps by drifting through particularly dense patches of the galaxy's dark matter halo? Every new observation peels back another layer of mystery, but one thing's clear: the Pinwheel's dark globulars aren't just astrophysical oddities. They're cosmic breadcrumbs leading us toward answers about dark matter's true nature and the hidden stories of how galaxies like ours were built, one invisible piece at a time. In the Pinwheel Galaxy's outer reaches, a cosmic butterfly spreads its glowing wings, a planetary nebula so exquisitely symmetrical, it defies the very star that birthed it. Catalogued as PN 672, this delicate structure of ionized gas shouldn't exist, not because planetary nebulae are rare, but because its central star, a dim, unremarkable white dwarf, lacks the energy and stellar winds needed to sculpt such perfection. It's like finding a Renaissance masterpiece painted by a toddler. The artistry far exceeds the creator's apparent capabilities. Planetary nebulae typically form when aging stars shed their outer layers, leaving behind a hot core that lights up the expelled gas like a fluorescent sign. The most stunning examples, like the Ring Nebula, owe their intricate shapes to complex interactions between stellar winds, magnetic fields, and binary companions. But PN 672 central star is alone, quiet, and surprisingly cool for a nebula this vibrant. Spectroscopic analysis reveals it's just 12,000 degrees Celsius, half the temperature needed to produce the ultraviolet radiation required to make the nebula glow this intensely. It's akin to a light bulb too dim to illuminate a room, yet somehow casting shadows across the street. So how did this cosmic contradiction come to be? One theory points to a hidden accomplice, an unseen companion star or substellar object that might have turbocharged the nebula's formation. If the central white dwarf once orbited a more massive partner, their gravitational dance could have flung gas outward in precise patterns before one star vanished, either collapsing into a black hole or fading into obscurity. Imagine two dancers spinning with a ribbon between them. If one suddenly lets go, the ribbon flies outward in a graceful arc. But Hubble observations show no gravitational wobbles in the white dwarf's motion, leaving the mystery unsolved. Another possibility rewrites the rules of stellar aging. The nebula's chemical composition holds peculiar clues: unusually high levels of nitrogen and oxygen arranged in concentric shells, like layers in a celestial onion. This suggests the central star might have undergone thermal pulses, brief periods of late-stage nuclear fusion that blasted material away in waves. Normally, such pulses create chaotic, uneven nebulae, but if the star's magnetic field was unusually strong, it could have funneled these ejections into orderly streams, sculpting the gas into its current, improbable symmetry. Picture a fire hose spraying water in all directions, only for an invisible hand to shape the spray into a perfect sphere. The most tantalizing explanation lies in the nebula's extreme youth. Radio measurements suggest PN 672 is barely 900 years old, a newborn by cosmic standards. Its crisp structure might simply reflect that we're catching it at a fleeting moment when the gas hasn't had time to disperse or collide with interstellar material. But even this can't fully explain the nebula's brilliance. Some astronomers speculate the star could have ejected an unusually dense shell of gas right before becoming a white dwarf, like a final, desperate exhalation. When the star's UV light finally hit this dense shell, it might have lit up with unexpected intensity, a last hurrah amplified by perfect timing. What makes this impossible nebula so captivating isn't just its defiance of physics, it's the questions it raises about how many other cosmic outliers we've missed. If stars can create such breathtaking structures under unlikely conditions, our models of stellar deaths might need re-evaluating. Every flicker of PN 672 gas whispers a challenge. Sometimes the universe's most beautiful creations emerge not despite the rules, but because we haven't yet discovered all the rules there are. From its eerily silent black hole to runaway star clusters hurtling through space, the Pinwheel Galaxy is a cosmic hall of mirrors, each reflection more bewildering than the last. We've wandered through its warped spiral arms, where stars vanish without supernovas and dust lanes fray like snipped threads. We've stood at the edge of its lopsided halo, where ghostly stellar streams whisper tales of ancient collisions, and peered into its frozen gas clouds, where molecules assemble life's ingredients in deep space freezers. This galaxy doesn't just break the rules, it rewrites them in real time, leaving astronomers scrambling to decode its contradictions. Consider the staggering range of oddities we've uncovered. Gamma-ray hotspots with no visible source, pulsars that glitch like broken clocks, and planetary nebulae shining too brightly for their faint stellar engines. There are the mirror star clusters identical down to their chemistry, yet born billions of years apart, and the eerie dead zones where star formation simply stopped. The Pinwheel's polar ring debris suggests a violent past, while its misaligned magnetic fields reveal hidden forces shaping its present. And let's not forget the ticking time bomb WR-142, a Wolf-Rayet star poised to unleash a gamma-ray burst that could outshine entire galaxies. What makes these 30 phenomena so extraordinary isn't just their individual strangeness, it's how they collide to paint a picture of a galaxy that refuses to be categorized. The Pinwheel's quiet core defies expectations for spiral galaxies, while its shortage of dark matter upends cosmological models. Its ultraluminous X-ray sources could be missing link black holes, and its hypervelocity clusters challenge our understanding of gravitational slingshots. Even its youngest features, like the potential tidal dwarf galaxy forming right now, hint at processes we've never witnessed elsewhere. This whirlpool of stars isn't just a pretty face in the cosmos. It's a laboratory, a puzzle box, and a time capsule all at once. Every observation peels back another layer, revealing how much we still don't know about the forces shaping galaxies. The Pinwheel's greatest lesson: the universe is far stranger, more inventive, and more unpredictable than our textbooks ever imagined. Now it's your turn. Which of these 30 mysteries left you utterly spellbound? Was it the star that disappeared without a trace, the rogue black hole hiding in plain sight, or the frozen clouds where life's building blocks assemble in the dark? Drop your pick in the comments below. We're obsessed with hearing which cosmic head-scratcher keeps you up at night. And if you're hungry for more deep space enigmas, hit that subscribe button. The universe is brimming with unsolved wonders, and we're just getting started. Until next time, keep looking up. You never know what secrets the next galaxy might reveal.